Parallel universes have captured human imagination for decades, but here's what will shock you. The mathematics of quantum physics doesn't just suggest they might exist, it practically demands they do. And even more incredible, we might actually be able to detect them. I'm about to take you on a journey through the most mind-bending concepts in modern science. We'll explore quantum experiments, so strange they seem like magic, mathematical proofs that suggest infinite versions of reality, and cutting-edge research that could revolutionize everything we think we know about existence itself. But first, let me tell you something that happened in a laboratory in 1909 that changed everything. A physicist named Thomas Young performed what seemed like a simple experiment with light and two slits in a barrier. What he discovered was so bizarre, so fundamentally impossible according to our everyday understanding of reality, that it launched a century-long quest to understand the true nature of existence. That experiment revealed something terrifying and beautiful. Reality as we experience it might be just one thread in an infinite tapestry of parallel worlds, each as real as the one you're living in right now. The implications are staggering. If parallel universes exist, then every choice you've ever made, every path not taken, every what-if scenario that's ever crossed your mind is playing out somewhere in the multiverse. There's a reality where you became a professional athlete, another where you never met your best friend, and countless others where history itself unfolded completely differently. But here's the kicker. We're not just talking about philosophical possibilities anymore. Scientists are developing actual experiments, real tests that could prove parallel universes exist within the next decade. The technology is getting close enough that we might finally answer the ultimate question about reality itself. Throughout this investigation, I'll show you exactly how quantum mechanics breaks down the walls between possible and impossible. You'll see mathematical equations that predict infinite copies of you, and you'll discover why some of the smartest people on Earth are convinced that parallel universes aren't just real, but detectable. The journey starts with understanding why reality at the quantum level operates by rules so strange they seem designed by someone with a twisted sense of humor. When you shrink down to the scale of atoms and subatomic particles, the comfortable, predictable world we know completely falls apart. At the quantum level, particles don't behave like tiny billiard balls following predictable paths. Instead, they exist in what scientists call superposition, simultaneously occupying multiple states until the moment someone observes them. It's as if a coin could spin in the air forever, being both heads and tails at the same time, only choosing one when you catch it. This isn't just theoretical weirdness. Scientists have proven this experimentally thousands of times. Electrons can spin in multiple directions simultaneously. Photons can take several different paths at once. Particles can even be in multiple locations at the same time, existing as ghostly probability clouds rather than solid objects. The famous double-slit experiment demonstrates this perfectly. When you fire individual photons at a barrier with two slits, each photon somehow goes through both slits simultaneously, creating an interference pattern that's only possible if the photon interfered with itself. But the moment you try to detect which slit the photon actually went through, the interference pattern disappears, and the photon behaves like a normal particle going through just one slit. This observation effect is where things get truly mind-bending. The universe seems to know when it's being watched. The act of measurement doesn't just reveal reality, it appears to create it. Before observation, quantum systems exist in superposition. After observation, they collapse into definite states. But here's the question that's haunted physicists for nearly a century. What happens to all those other possible states when the quantum system collapses? Where do they go? Do they simply disappear into nothingness? Or do they continue existing somewhere else? Hugh Everett III proposed an answer in 1957 that was so radical it got him essentially blacklisted from the physics community. He suggested that quantum systems never actually collapse. Instead, every possible outcome of every quantum measurement occurs simultaneously in separate, parallel universes. When you observe a spinning coin and see heads, there's another universe where another version of you observes tails. This is the many worlds interpretation of quantum mechanics, and it's not some fringe theory anymore. It's taken seriously by many leading physicists because it solves several major problems with traditional quantum mechanics while making testable predictions. Think about the implications. Every quantum event that could go multiple ways does go multiple ways, just in different universes. The radioactive atom that might decay creates two universes, one where it decays and another where it doesn't. The electron that could spin up or down creates parallel realities for each possibility. This process happens continuously, at every moment, on every scale, throughout the entire universe. Quantum events occur trillions of times per second in every cubic inch of space. Each one potentially spawns new parallel universes, creating an infinite tree of branching realities that grows exponentially every instant. The mathematics of many worlds is elegant and consistent, but the philosophical implications are staggering. If true, then every decision you've ever made created parallel universes where you made different choices. Every accident that almost happened did happen somewhere else. Every person who almost existed does exist in some parallel reality. There's a universe where World War II never occurred, another where dinosaurs never went extinct, and countless others where the fundamental constants of physics are slightly different, creating realities with entirely different physical laws. The multiverse doesn't just contain variations of our world, it contains every possible world that quantum mechanics allows. But wait, if these parallel universes exist, why can't we see them or interact with them? The answer lies in something called decoherence. As quantum systems interact with their environment, they become entangled with larger and larger systems, making the different parallel universes increasingly isolated from each other. Imagine two soap bubbles touching. Initially, they might exchange some material at the boundary, but as they separate, they become completely independent. Parallel universes work similarly. They might start from the same quantum event, but as they evolve, they become causally disconnected, unable to influence each other. This isolation explains why we experience only one consistent reality instead of a confusing mixture of parallel possibilities. Our consciousness follows one particular branch of the universal wave function, unaware of all the other branches where different versions of us are having different experiences. However, and this is crucial, the isolation might not be perfect. Under very specific circumstances, parallel universes might still interact in subtle ways that could potentially be detected by sufficiently sensitive experiments. This possibility has sparked intense research into ways we might actually prove the existence of the multiverse. The search for parallel universe evidence requires understanding quantum interference on macroscopic scales. While individual particles routinely demonstrate quantum effects, larger objects typically lose their quantum properties through interaction with the environment. But scientists are developing techniques to maintain quantum coherence in increasingly large systems. Recent experiments have demonstrated quantum superposition in objects containing billions of atoms. Researchers have created quantum states in tiny mirrors, microscopic diamonds, and even living bacteria. As these techniques improve, we might eventually be able to create macroscopic quantum states large enough to potentially interact with parallel versions of themselves. The key insight is that if parallel universes exist, they should occasionally interfere with our universe in ways that produce detectable quantum effects. These effects would be incredibly subtle, requiring extraordinary precision to measure, but they would provide definitive proof that we're not alone in the multiverse. Consider what this means for human consciousness and identity. If parallel universes are real, then your sense of being a unique individual might be an illusion. There could be countless versions of you, each with slightly different experiences, making slightly different choices, living slightly different lives. Yet each version would feel just as uniquely you as you do right now. Some versions of you might be reading this exact sentence at this exact moment, while others stopped watching minutes ago, and still others never encountered this video at all. The version of you experiencing these words is just one thread in an infinite tapestry of parallel selves, each equally real and equally convinced of their own singular existence. This raises profound questions about free will and responsibility. If every possible choice creates a universe where you make that choice, do your decisions really matter? Or are you simply experiencing one predetermined path through the quantum multiverse, with other versions of you experiencing all the alternatives? The answer might be that choice and determinism coexist in the multiverse. While every possibility occurs somewhere, the version of you making choices still experiences genuine agency within your particular branch of reality. Your decisions matter to you and everyone in your universe, even if other versions of those people experience different outcomes elsewhere. But the implications extend far beyond philosophy into practical questions about the nature of scientific discovery itself. If parallel universes exist, then scientific breakthroughs aren't just happening in our reality. Every major discovery, every revolutionary insight, every moment of genius is occurring simultaneously across countless parallel worlds. There might be universes where Einstein never developed relativity, others where quantum mechanics was discovered centuries earlier, and realities where entirely different branches of physics dominate our understanding of the cosmos. This creates a fascinating puzzle. Are we discovering fundamental truths about reality, or are we simply following one particular path through an infinite maze of possible scientific developments? The equations we consider universal laws might be unique to our branch of the multiverse, while parallel versions of humanity develop completely different mathematical frameworks to describe their versions of reality. The implications for technology are equally mind-bending. In some parallel universe, researchers might have already cracked the code for detecting other realities. They could be watching us right now, studying our universe like we study distant galaxies. Meanwhile, in other realities, humanity might never have developed the scientific method at all, remaining forever unaware of the quantum nature of existence. But here's where things get really interesting. If we can detect parallel universes, we might also be able to extract information from them. Imagine accessing the collective knowledge of infinite versions of human civilization. Every problem we face, every challenge that seems insurmountable, has already been solved somewhere in the multiverse. Cancer, climate change, poverty, aging, death itself. Somewhere in the vast expanse of parallel realities, versions of humanity have conquered every obstacle we can imagine. The question isn't whether solutions exist, but whether we can develop the technology to peer across dimensional barriers and learn from our parallel selves. Several research teams are already working on this possibility. They're developing quantum computers designed not just to process information, but to potentially access computational resources from parallel universes. The idea sounds like science fiction, but the mathematics checks out. If parallel worlds exist, and quantum systems can interact across dimensional boundaries, then we might be able to harness the processing power of infinite parallel computers. David Deutsch, one of the pioneers of quantum computing, has suggested that quantum computers work precisely because they can access parallel universes. When a quantum computer solves a complex problem, it might be distributing the calculation across countless parallel versions of itself, each working on a different part of the solution simultaneously. This would explain why quantum computers can solve certain problems exponentially faster than classical computers. They're not just using the atoms in our universe to compute. They're borrowing computational resources from the entire multiverse, effectively turning every quantum calculation into a collaboration between infinite parallel realities. The experimental evidence for this idea is starting to accumulate. Quantum computers consistently outperform classical computers in ways that suggest they have access to computational resources that shouldn't exist if our universe were the only reality. The speed-up is too dramatic, too consistent, to be explained by conventional physics operating within a single universe. But detecting parallel universes requires more than just indirect evidence from quantum computers. Scientists need direct proof that other realities exist, and surprisingly, several experimental approaches might make this possible within the next decade. The first approach involves creating quantum systems large enough to potentially interact with their parallel counterparts. If researchers can maintain quantum coherence in objects approaching macroscopic size, they might detect interference patterns that could only be caused by interaction with parallel versions of those objects. Recent breakthroughs in quantum isolation have made this increasingly feasible. Scientists have successfully demonstrated quantum effects in objects containing trillions of atoms, and the scale is increasing rapidly. Within a few years, experiments might achieve quantum coherence in objects visible to the naked eye. The second approach focuses on cosmic scale detection. Some theories suggest that parallel universes might occasionally collide or interact at the cosmic level, leaving detectable signatures in the cosmic microwave background radiation. Advanced telescopes and data analysis techniques are already searching for these signatures, looking for patterns that could only be explained by interaction with other realities. The third approach is perhaps the most ambitious. It involves using quantum entanglement to create communication channels between parallel universes. While this sounds impossible, the mathematics of quantum mechanics doesn't explicitly forbid it. If scientists can create quantum systems that remain entangled across parallel realities, they might be able to send simple signals between different versions of our universe. Imagine receiving a message from a parallel version of Earth where history unfolded differently. A reality where different scientific discoveries were made, where different technologies were developed, where humanity took alternative paths through the challenges of existence. The knowledge exchange could revolutionize our understanding of everything from physics to philosophy. But even without direct communication, simply proving that parallel universes exist would transform human civilization. It would confirm that consciousness, identity, and reality itself are far stranger and more wonderful than we ever imagined. Every person you've ever known exists in countless variations across infinite realities. Every moment you've experienced is just one possibility among endless alternatives. The search for parallel universes is accelerating rapidly. New experiments are being designed, new technologies are being developed, and new theoretical frameworks are being constructed to guide the search. The question isn't whether we'll find evidence of parallel realities, but when. Some researchers believe we're less than a decade away from definitive proof. Others think it might take longer, but few doubt that the evidence will eventually emerge. The mathematics is too compelling, the experimental possibilities too promising, and the technological progress too rapid for parallel universes to remain hidden much longer. When that proof arrives, it will mark one of the most significant moments in human history. We'll discover that our universe, vast as it seems, is just one thread in an infinite tapestry of realities. Every question we've ever asked about existence will need to be reconsidered in light of the multiverse. But the discovery will also raise new questions that are even more profound. If infinite parallel universes exist, what determines which one we experience? Is consciousness somehow special, able to select which reality it observes from the infinite possibilities? Or are we simply along for the ride, experiencing one arbitrary path through the quantum multiverse without any special role or significance? These questions touch on the deepest mysteries of existence itself. They probe the relationship between mind and reality, between observer and observed, between the possible and the actual. Finding answers will require not just new experiments and technologies, but entirely new ways of thinking about consciousness, identity, and the nature of existence. The implications extend beyond science into every aspect of human culture and understanding. Religion, philosophy, ethics, art, literature, everything we've created as a species will need to be reconsidered in light of the multiverse. How do we find meaning in a reality where every possible story is being told somewhere? How do we make moral choices when every alternative choice is also being made by parallel versions of ourselves? Perhaps the answer is that meaning doesn't require uniqueness. Love, compassion, creativity, and wonder are just as valuable whether they occur in one universe or infinite universes. The fact that parallel versions of our experiences might exist elsewhere doesn't diminish the reality and significance of what we experience here and now. In fact, the existence of parallel universes might make our experiences more precious, not less. Knowing that infinite variations exist could help us appreciate the specific, unique path that our particular branch of reality has taken. Every moment becomes special precisely because it's our moment, experienced by our version of consciousness in our particular universe. The search for parallel universes continues, driven by human curiosity and the irresistible desire to understand our place in the cosmos. Whether we find them or not, the search itself reveals something profound about human nature. We are beings who cannot rest content with simple answers, who must push the boundaries of knowledge and understanding, who dare to ask questions about the very nature of reality itself. And maybe, just maybe, somewhere in a parallel universe, another version of you is asking the same questions and discovering the same truths. The multiverse, if it exists, is vast enough to contain every wonder we can imagine, and many we cannot. The journey to find it has only just begun. The technology needed to detect parallel universes already exists in primitive form, scattered across laboratories around the world. Quantum interferometers that can measure distortions smaller than a fraction of a proton's width, superconducting circuits that maintain quantum coherence for record-breaking durations, particle accelerators that probe the fundamental structure of reality at energies approaching those present at the birth of the universe. But here's what most people don't realize. These aren't separate technologies developed for different purposes. They're pieces of a larger puzzle, components of a detection system that could revolutionize our understanding of existence within your lifetime. The key breakthrough came in 2019 when researchers at Yale University created something that shouldn't exist according to classical physics. They built a quantum system large enough to see with the naked eye that maintained superposition for over a minute. A tiny aluminum drum, invisible to you but massive on the quantum scale, simultaneously vibrating and not vibrating until observed. This achievement shattered the boundary between quantum weirdness and everyday reality. For the first time in history, scientists demonstrated that macroscopic objects could exist in multiple states simultaneously, just like subatomic particles. The implications were staggering, but the media barely noticed. They had no idea they were witnessing the first step toward detecting parallel universes. The aluminum drum experiment proved that quantum effects could be scaled up far beyond what anyone thought possible. If a mechanical object containing billions of atoms could exist in superposition, then much larger systems might also demonstrate quantum behavior under the right conditions. This opened a pathway to experiments that could potentially detect interactions between parallel realities. But scaling up quantum effects requires solving an almost impossible challenge: environmental noise. Every vibration, every stray photon, every thermal fluctuation threatens to destroy the delicate quantum states needed for parallel universe detection. It's like trying to hear a whisper during a hurricane while wearing earplugs and standing next to a jet engine. Scientists call this challenge the decoherence problem, and it's the primary obstacle preventing us from detecting parallel worlds. Quantum systems naturally want to interact with their environment, and once they do, their ability to maintain superposition disappears almost instantly. The larger the quantum system, the faster decoherence occurs. However, researchers have developed ingenious methods to combat decoherence. They use supercooled environments approaching absolute zero temperature. They employ electromagnetic shielding that blocks external interference. They create vacuum chambers more empty than interstellar space. They've even developed active feedback systems that continuously monitor and correct for environmental disturbances. These techniques have enabled quantum coherence in increasingly large systems. What started with individual atoms has progressed to molecules, then to microscopic crystals, and now to mechanical devices visible under a microscope. Each advance brings us closer to the scale needed for parallel universe detection. The mathematics suggests that once quantum systems reach a critical size threshold, they should begin to exhibit interference patterns that can only be explained by interaction with parallel versions of themselves. This threshold varies depending on the specific experimental setup, but current estimates suggest it might be achievable within the next 5 to 10 years. Several research groups are racing toward this goal using different approaches. Some focus on creating larger and larger quantum superpositions, pushing the boundaries of what's possible with current technology. Others work on extending the duration of quantum coherence, keeping systems in superposition for longer periods. Still, others develop new types of quantum states that might be more resistant to decoherence. The competition is intense because the stakes are enormous. The first laboratory to demonstrate parallel universe detection would achieve one of the greatest scientific breakthroughs in human history. Nobel Prizes would be inevitable, but more importantly, the discovery would fundamentally change our understanding of reality itself. One particularly promising approach involves quantum mirrors. These are microscopic reflective surfaces that can be placed in quantum superposition, simultaneously reflecting and transmitting light. If parallel universes exist, light bouncing off a quantum mirror should occasionally interfere with light from parallel versions of the same experiment. The interference pattern would be incredibly subtle, requiring measurement precision beyond anything currently achievable. But theoretical calculations suggest it should be detectable using advanced versions of equipment that already exists. The challenge lies in isolating the parallel universe signal from all the noise and uncertainty inherent in quantum measurements. Another approach focuses on quantum computers themselves. If these devices really do access computational resources from parallel universes, then carefully designed algorithms might be able to detect evidence of this cross-dimensional computation. By analyzing the specific patterns of quantum interference in quantum computer operations, researchers might identify signatures that could only come from parallel realities. This computational approach has several advantages. Quantum computers are already being built at increasing scale and sophistication. The detection techniques would use existing hardware rather than requiring entirely new experimental apparatus, and the results could be verified through repetition and statistical analysis, providing the robust evidence needed to convince the scientific community. But perhaps the most ambitious approach involves cosmic-scale detection. Some theoretical models predict that parallel universes might occasionally interact or collide at the cosmic level, leaving detectable signatures in the structure of our universe. These signatures would be incredibly faint, requiring analysis of vast amounts of astronomical data using artificial intelligence systems to identify patterns that human researchers might miss. The search for cosmic parallel universe signatures has already begun. Advanced telescopes survey the cosmic microwave background radiation, looking for anomalies that might indicate interaction with other realities. Gravitational wave detectors monitor spacetime itself for ripples that could be caused by parallel universe collisions. Dark matter experiments probe for particles that might be leaking between dimensions. None of these cosmic searches have found definitive evidence yet, but the sensitivity and scope of the observations continue to improve. New telescopes with unprecedented resolution are coming online. Gravitational wave networks are expanding globally. Dark matter detection techniques are becoming more sophisticated every year. The timeline for discovery remains uncertain, but the momentum is building rapidly. Experimental capabilities that seemed impossible just a decade ago are now routine. Quantum systems that physicists could only dream about are being built in laboratories around the world. The theoretical framework for parallel universe detection is becoming increasingly refined and testable. Meanwhile, the implications of potential discovery continue to ripple through scientific and philosophical communities. If parallel universes exist and can be detected, what does this mean for our understanding of consciousness, free will, and personal identity? How would society adapt to knowing that every possible version of history is playing out simultaneously somewhere in the multiverse? These questions become more pressing as detection becomes more feasible. Religious leaders, philosophers, ethicists, and policymakers are beginning to grapple with scenarios that once existed only in science fiction. How do you maintain moral responsibility in a multiverse where every possible choice is made by some version of yourself? How do you find meaning and purpose when infinite variations of your life exist across parallel realities? Some argue that parallel universes would make life more meaningful, not less. Every choice would matter because it determines which specific branch of the multiverse you experience. Every moment would be precious because it represents your unique path through infinite possibilities. The knowledge that other versions exist might help us appreciate the particular reality we inhabit. Others worry about psychological and social impacts. How would people react to learning that their loved ones exist in countless variations across parallel universes? Would this knowledge provide comfort in the face of loss, or would it create existential anxiety about the nature of identity and relationships? The debate extends into practical considerations. If parallel universe detection becomes possible, should the experiments proceed? Would the knowledge gained justify the potential risks to human psychology and social stability? Some argue that humanity has a responsibility to pursue truth regardless of consequences. Others advocate for careful consideration of the broader implications before moving forward, but the scientific momentum may be unstoppable. Too many research groups in too many countries are pursuing parallel universe detection for any coordinated halt to be practical. The experiments will likely proceed regardless of philosophical concerns, driven by scientific curiosity and the competitive dynamics of modern research. The race to detect parallel universes represents more than just another scientific advance. It embodies humanity's deepest drive to understand our place in the cosmos, to push beyond the boundaries of the known and discover truths that transform our entire worldview. Whether we're ready or not, the answer to one of existence's most profound questions may be just around the corner. The next few years will likely determine whether parallel universes remain in the realm of speculation or become established scientific fact. The experiments are being designed, the equipment is being built, and the theoretical framework is being refined. Somewhere in a laboratory, perhaps at this very moment, a quantum system might be interacting with its parallel counterpart, generating the first detectable evidence that we are not alone in the multiverse. And if that evidence emerges, everything changes. Our understanding of reality, consciousness, identity, and existence itself will need to be completely reconsidered. We'll discover that our universe, vast and ancient as it seems, is just one thread in an infinite tapestry of parallel realities, each as real and significant as our own. The implications stretch beyond science into every aspect of human experience. Art, literature, philosophy, religion, ethics, politics, all will be transformed by the knowledge that infinite variations of human experience exist across parallel worlds. We'll face questions about meaning and purpose that our species has never had to confront, but we'll also discover that we're part of something far grander and more mysterious than we ever imagined. The universe won't just be the stage where human drama plays out. It will be one of infinite stages, hosting infinite variations of every story we can conceive, and many we cannot. The search for parallel universes continues, driven by the same curiosity that led our ancestors to explore new continents and peer through the first telescopes at distant stars. We are a species that cannot rest content with simple answers, that must always push further into the unknown, that dares to ask questions about the very nature of reality itself. And perhaps, somewhere in a parallel universe, another version of humanity is asking the same questions and making the same discoveries. The multiverse, if it exists, is vast enough to contain every wonder we can imagine and infinite wonders we cannot. The journey to understand it has only just begun, but the destination may be closer than we think. The technology exists, the theories are testable, the experiments are being designed. Within your lifetime, we may finally answer the ultimate question about the nature of existence itself. Are we alone in our universe, or are we part of an infinite community of parallel realities, each as real and significant as our own? The answer is coming, and it will change everything we thought we knew about what it means to exist. The breakthrough moment might happen in a place you'd never expect. Not in some massive particle accelerator or billion-dollar observatory, but in a basement laboratory at a university where graduate students work late into the night, adjusting laser alignments and monitoring quantum states that exist for mere milliseconds before dissolving back into ordinary reality. This is where the real work happens, where theories meet the brutal honesty of experimental data, where brilliant minds confront the fundamental weirdness of quantum mechanics with instruments so sensitive they can detect the gravitational influence of a person walking past the building 3 floors above. The challenge these researchers face would seem impossible to anyone outside the field. They need to create quantum systems large enough to potentially interact with parallel versions of themselves, while simultaneously isolating those systems from every source of interference in the known universe. It's like trying to balance a pencil on its point during an earthquake while blindfolded. But here's what makes this pursuit so compelling. The mathematics doesn't just suggest parallel universe detection is possible, it provides a roadmap. The equations tell us exactly what to look for, precisely how the signals should behave, and specifically what experimental conditions are required. We're not shooting in the dark anymore. We're following a blueprint written in the language of quantum mechanics itself. Recent advances in quantum error correction have solved problems that seemed insurmountable just 5 years ago. Researchers can now maintain quantum coherence in systems containing millions of entangled particles. They've created quantum networks that remain stable for hours instead of microseconds. They've even demonstrated quantum effects in objects warm enough to touch, breaking the assumption that quantum behavior requires temperatures near absolute zero. These achievements represent more than incremental progress. They're exponential leaps that compress decades of anticipated development into mere years. The timeline for parallel universe detection keeps accelerating as each breakthrough enables the next breakthrough in an accelerating cascade of discovery. The most promising experiments now under development use a technique called quantum amplification. Instead of trying to detect the incredibly weak signals from parallel universe interactions directly, researchers amplify these signals through carefully designed quantum processes that magnify the effects while preserving their distinctive signatures. Think of it like using a microscope to see bacteria. The bacteria exist whether you can see them or not, but the microscope makes their presence observable. Quantum amplification works similarly, taking interactions that are too subtle to detect directly and making them visible through sophisticated enhancement techniques. The amplification process is extraordinarily complex, requiring precise control of quantum states at multiple scales simultaneously. Researchers must coordinate the behavior of individual photons with macroscopic mechanical oscillators while maintaining quantum coherence across the entire system. It's like conducting an orchestra where every musician is invisible and the slightest mistake causes the entire performance to collapse into noise. But when everything works correctly, the results should be unmistakable. Quantum amplification can theoretically increase parallel universe signals by factors of millions or billions, bringing them well above the threshold of detectability. The challenge lies in distinguishing genuine parallel universe interactions from the countless other quantum effects that could produce similar signatures. This is where artificial intelligence becomes crucial. The patterns that indicate parallel universe interaction are so complex and subtle that human researchers couldn't identify them even if they were staring directly at the data. Machine learning systems trained on theoretical predictions can analyze vast amounts of experimental data, searching for correlations and anomalies that would be invisible to conventional analysis. Several research groups have already deployed AI systems specifically designed for parallel universe detection. These algorithms continuously monitor quantum experiments, looking for statistical patterns that match theoretical predictions for cross-dimensional interactions. The systems are becoming increasingly sophisticated, incorporating deep learning techniques that can identify previously unknown signatures of parallel universe activity. The AI approach has another crucial advantage. It can analyze multiple experiments simultaneously, looking for correlations between different laboratories and different experimental approaches. If parallel universes exist, they should produce consistent signatures across all types of quantum systems. This consistency would provide the robust evidence needed to convince the scientific community that the effects are real. But artificial intelligence also introduces new challenges. How do we verify that AI systems are correctly identifying parallel universe signals rather than finding spurious patterns in random data? Machine learning algorithms are notorious for discovering correlations that seem meaningful but are actually coincidental. Distinguishing genuine discovery from algorithmic artifacts requires careful validation and multiple independent confirmations. The solution involves creating what researchers call adversarial verification systems. Multiple AI algorithms compete against each other, with some designed to find parallel universe signatures and others designed to debunk false positives. Only signals that survive this adversarial process are considered potentially genuine, providing a rigorous filter against experimental and algorithmic errors. Meanwhile, theoretical physicists continue refining their predictions for what parallel universe detection should look like. The mathematics has evolved far beyond the original many worlds interpretation, incorporating insights from string theory, quantum field theory, and cosmology. Modern theoretical frameworks make increasingly specific predictions about the types of signals that should emerge from cross-dimensional interactions. These predictions vary depending on the exact nature of parallel universe connections. Some theories suggest that interactions should be strongest during quantum measurements, creating brief windows when parallel realities influence each other. Others predict continuous weak coupling that produces cumulative effects over extended periods. Still, others propose that interactions occur only under very specific conditions that researchers must learn to create artificially. The diversity of theoretical predictions actually strengthens the experimental program. Instead of looking for one specific type of signal, researchers can test multiple theoretical frameworks simultaneously. Each successful detection would not only prove parallel universes exist, but also reveal which theoretical approach best describes their behavior. This multi-theory approach has led to increasingly sophisticated experimental designs. Modern parallel universe detection experiments incorporate multiple measurement techniques, quantum state preparations, and analysis methods within single apparatus. They're designed to be sensitive to various types of cross-dimensional interactions while maintaining the precision needed to distinguish genuine signals from background noise. The scale of these experiments continues to grow as funding agencies recognize the potential significance of parallel universe detection. National laboratories are dedicating major resources to the effort. International collaborations are forming to share expertise and coordinate observations. Private foundations are supporting theoretical research and technological development. But perhaps most importantly, a new generation of physicists is entering the field with parallel universe detection as their primary research focus. These researchers grew up with quantum mechanics as established fact rather than revolutionary theory. They approach parallel universe detection with the same matter-of-fact attitude that previous generations applied to atomic physics or molecular biology. This generational shift is crucial because parallel universe detection requires a different mindset from traditional physics research. Instead of studying phenomena that definitely exist, researchers must develop experimental techniques sensitive enough to detect phenomena that might not exist at all. The psychological challenges are as significant as the technical ones. Young researchers seem better adapted to this uncertainty. They've grown up in a world where quantum weirdness is commonplace, where computers routinely exploit quantum effects, where the boundaries between possible and impossible are constantly shifting. They approach parallel universe detection not as a philosophical question, but as an engineering challenge. Their confidence is infectious and appears to be accelerating progress throughout the field. Senior researchers who were skeptical about parallel universe detection just a few years ago are now actively participating in experimental programs. The theoretical community has shifted from asking whether parallel universes exist to asking how we can detect them most efficiently. This momentum is creating a feedback loop that drives increasingly ambitious experiments. Success breeds success as each advancement enables more sophisticated follow-up studies. The field has reached a critical mass where progress becomes self-sustaining and accelerating. But success also brings new responsibilities. As parallel universe detection becomes more feasible, researchers must grapple with the broader implications of their work. The discovery of parallel realities would affect far more than just physics. It would touch every aspect of human understanding, from the nature of consciousness to the meaning of existence itself. Some research groups have begun incorporating philosophers, ethicists, and social scientists into their experimental teams. These collaborations help ensure that parallel universe research proceeds with appropriate consideration for its potential impacts on human society and culture. The goal is not just to detect parallel realities, but to do so in ways that help humanity adapt constructively to the knowledge. The ethical dimensions become more complex when considering the possibility of communication with parallel universes. If detection is possible, might information exchange also be achievable? Could we learn from parallel versions of human civilization that made different choices and achieved different outcomes? These questions push beyond current experimental capabilities, but they're not pure speculation. Several theoretical papers have outlined possible approaches to parallel universe communication, building on the same quantum mechanical principles that enable detection. The mathematics suggests that information transfer might be possible, though it would require technologies far more advanced than current detection experiments. The prospect of parallel universe communication raises profound questions about intellectual property, cultural exchange, and even warfare. If infinite versions of human civilization exist, they would presumably have developed different technologies, different solutions to common problems, and different approaches to social organization. The potential benefits of accessing this knowledge are obvious, but so are the risks. How would our economy function if we could access technologies from parallel realities where different scientific discoveries were made? How would our political systems adapt to knowledge of alternative forms of government that might be more effective than anything we've developed? How would our culture evolve through exposure to infinite variations of human creative expression? These questions may seem premature, but the rapid pace of experimental progress suggests they could become relevant sooner than expected. The gap between parallel universe detection and communication might be much smaller than initially anticipated. Researchers working on detection experiments are already thinking about how their techniques might be extended to enable information exchange. But first comes proof of existence. Despite all the theoretical framework and experimental progress, parallel universes remain unproven. The scientific community requires extraordinary evidence for extraordinary claims, and parallel universe detection certainly qualifies as extraordinary. The evidence must be reproducible, verifiable, and consistent across multiple independent experiments. It must eliminate all possible alternative explanations and demonstrate effects that could only be caused by interaction with parallel realities. The bar is set incredibly high, as it should be for a discovery that would revolutionize our understanding of existence itself. Meeting this evidentiary standard will require not just one breakthrough experiment, but a systematic program of increasingly sophisticated observations. Each positive result must be confirmed by independent research groups using different techniques and equipment. The accumulation of evidence must be overwhelming and undeniable. The process will likely take years even after the first positive detection. Science moves deliberately when confronting paradigm-shifting discoveries, subjecting every claim to rigorous scrutiny and demanding multiple confirmations before accepting revolutionary conclusions. The scientific community learned this lesson from previous episodes, where preliminary results that seemed groundbreaking ultimately proved to be experimental errors or misinterpretations. But the systematic nature of this verification process also provides confidence. When the scientific community finally accepts parallel universe detection as established fact, the evidence will be absolutely solid. There will be no room for doubt or alternative interpretation. The existence of parallel realities will be as well established as the existence of atoms or the expansion of the universe. That moment of acceptance will mark one of the greatest transitions in human intellectual history. We'll move from a species that wonders about parallel universes to a species that knows they exist. The shift in perspective will be profound and irreversible, changing not just how we think about physics, but how we think about ourselves and our place in the cosmos. The transition has already begun in research communities where parallel universe detection is treated as an engineering problem rather than a philosophical question. These researchers work with the assumption that parallel realities exist and focus their efforts on developing the technology needed to prove it. Their confidence shapes the entire field, creating an atmosphere of anticipation rather than skepticism. This anticipation is building throughout the broader scientific community as well. Conferences on parallel universe detection draw standing room-only crowds. Research papers on the topic receive unprecedented attention. Graduate students compete for positions in experimental programs focused on cross-dimensional detection. The excitement is palpable because everyone recognizes what's at stake. We're not just trying to detect another type of particle or measure another physical constant. We're attempting to answer one of the most fundamental questions about the nature of reality itself. The implications stretch far beyond physics into philosophy, theology, psychology, and every other domain of human thought. Success would confirm that our universe, vast as it seems, is just one reality among infinite possibilities. Every choice we've made, every path we've taken, every moment we've experienced, represents just one thread in an unimaginably complex tapestry of parallel existences. The knowledge would be simultaneously humbling and inspiring, diminishing our cosmic significance while expanding our understanding of what existence means. The search continues with growing intensity and sophistication. New experiments are being designed, new technologies are being developed, and new theoretical frameworks are being tested. The question is no longer whether we'll detect parallel universes, but when and how the detection will occur. Somewhere in a laboratory, perhaps at this very moment, a quantum system is maintaining coherence long enough to interact with its parallel counterpart. The signal might be incredibly weak, buried in noise and uncertainty, but it's there waiting to be discovered by sufficiently sensitive instruments and sufficiently clever analysis techniques. The discovery could happen tomorrow, or it could take another decade. But the trajectory is clear. We're moving inexorably toward proof of parallel realities, driven by scientific curiosity and enabled by rapidly advancing technology. The question that has fascinated humanity for generations is finally becoming answerable through rigorous experimental investigation. When the answer comes, it will transform everything we thought we knew about existence, consciousness, and our place in the cosmos. We'll discover that we're part of something far grander and more mysterious than we ever imagined. citizens of an infinite multiverse where every possibility is realized somewhere in the vast expanse of parallel realities. The journey toward this discovery represents humanity at its best, curious, determined, willing to question fundamental assumptions and pursue truth wherever it leads. We're using our finest instruments and sharpest minds to probe the deepest mysteries of existence, driven by an insatiable desire to understand the true nature of reality. And reality, it turns out, may be far stranger and more wonderful than we ever dared to imagine. The detection technology itself is evolving at a pace that would have seemed impossible just 5 years ago. Quantum sensors that once required entire rooms full of equipment are being miniaturized into devices small enough to fit on a desktop. Cooling systems that previously demanded massive infrastructure now operate with commercially available components. The barriers between theoretical possibility and practical implementation are dissolving faster than anyone anticipated. This miniaturization revolution is democratizing parallel universe research in ways that could accelerate discovery exponentially. Instead of requiring access to billion-dollar national laboratories, researchers at smaller institutions can now conduct meaningful experiments with budgets measured in hundreds of thousands rather than hundreds of millions of dollars. Graduate students are building quantum detection systems in university basements that rival the capabilities of major research facilities from just a decade ago. The distributed nature of this research creates a fascinating dynamic. Hundreds of independent experiments are running simultaneously around the world, each probing slightly different aspects of quantum reality. Some focus on mechanical systems, others on electromagnetic fields, still others on exotic states of matter that exist only at temperatures colder than deep space. The diversity of approaches increases the probability that someone, somewhere, will stumble upon the specific conditions needed for parallel universe detection. But stumbling isn't really the right word anymore. The theoretical framework has become so sophisticated that researchers can predict with remarkable precision what parallel universe interactions should look like under different experimental conditions. They know which quantum states are most likely to exhibit cross-dimensional coupling. They understand how environmental factors affect the strength and detectability of parallel universe signals. They've even developed mathematical models that optimize experimental parameters for maximum detection probability. This predictive power transforms parallel universe research from a fishing expedition into targeted hunting. Researchers aren't randomly trying different approaches and hoping for the best. They're systematically exploring parameter space, following theoretical roadmaps that guide them toward the most promising experimental configurations. Each negative result provides valuable information that helps refine the search strategy and improve the next iteration of experiments. The systematic approach is paying dividends in unexpected ways. Even experiments that fail to detect parallel universe interactions are producing breakthrough discoveries about the fundamental nature of quantum mechanics. Researchers are uncovering new types of quantum states, discovering previously unknown forms of quantum entanglement, and developing measurement techniques that push the boundaries of what's possible with current technology. These ancillary discoveries are valuable in their own right, but they also contribute to the ultimate goal of parallel universe detection. Each advance in quantum control and measurement brings the field closer to the sensitivity threshold needed to observe cross-dimensional interactions. Progress compounds as new techniques enable more sophisticated experiments that reveal new phenomena that inspire even more advanced approaches. The compound nature of this progress creates an interesting psychological dynamic within the research community. Individual experiments might not achieve their primary goal of detecting parallel universes, but they contribute to a larger effort that feels increasingly inevitable. Researchers maintain optimism and motivation even when their specific projects don't produce breakthrough results because they can see how their work fits into the broader trajectory toward discovery. This sustained motivation is crucial because parallel universe detection requires unprecedented levels of precision and persistence. The signals researchers are trying to detect exist at the very edge of what's theoretically possible to measure. Background noise from countless sources threatens to overwhelm the subtle effects they're seeking. Environmental disturbances that would be completely negligible in ordinary experiments can destroy the delicate quantum states needed for cross-dimensional detection. Success requires not just technical excellence, but almost obsessive attention to detail. Researchers spend months characterizing every possible source of interference in their laboratories. They map electromagnetic fields, catalog vibration patterns, monitor temperature fluctuations, and track air pressure changes. They build isolation systems within isolation systems, creating nested shells of protection around their quantum experiments. The level of environmental control required approaches the absurd. Some laboratories maintain temperature stability to within thousandths of a degree. Others eliminate vibrations so effectively that a person walking on the floor above the experiment would cause measurable disturbances. The most sensitive setups require researchers to coordinate their movements and activities to avoid disrupting measurements that might be happening several rooms away. But this extreme attention to environmental control is revealing unexpected insights about the nature of quantum systems themselves. Researchers are discovering that quantum states are far more robust and controllable than previously thought, provided that the right isolation techniques are employed. Systems that theorists predicted should lose coherence in microseconds are maintaining quantum properties for hours or even days under carefully controlled conditions. These extended coherence times open entirely new possibilities for parallel universe detection. The longer a quantum system maintains superposition, the more opportunity it has to interact with parallel versions of itself. Extended coherence also allows for more sophisticated measurement protocols that can extract weaker signals from background noise through long-duration averaging and correlation analysis. The measurement protocols themselves have become works of art, incorporating techniques borrowed from fields as diverse as radio astronomy, seismic monitoring, and medical imaging. Researchers use lock-in amplifiers to extract periodic signals from noise. They employ machine learning algorithms to identify subtle patterns in vast datasets. They develop custom electronics that can measure quantum effects while introducing minimal disturbance to the systems being observed. Perhaps most importantly, they're learning to work with quantum uncertainty rather than fighting against it. Traditional measurement approaches try to minimize quantum noise and eliminate uncertainty. Parallel universe detection requires embracing quantum uncertainty and using it as a resource rather than treating it as an obstacle. Researchers are developing techniques that exploit quantum uncertainty to amplify the very signals they're trying to detect. This philosophical shift represents a fundamental change in how physicists approach quantum experiments. Instead of trying to force quantum systems to behave classically, researchers are learning to think quantum mechanically from the ground up. They design experiments that work with quantum superposition, quantum entanglement, and quantum uncertainty as natural features rather than problematic complications. The shift in thinking is producing experimental designs that would have seemed impossible to previous generations of physicists. Quantum systems that simultaneously exist in multiple states are being used to probe multiple parallel universes at once. Entangled particles separated by large distances provide distributed detection networks that can identify parallel universe interactions across extended regions of space. Quantum feedback systems continuously adapt measurement protocols based on real-time analysis of quantum behavior. These advanced techniques are bringing parallel universe detection within reach of current technology, but they're also revealing just how strange and wonderful quantum reality truly is. The more researchers learn about quantum mechanics, the more convinced many become that parallel universes aren't just possible but inevitable consequences of the fundamental structure of reality. The conviction is spreading beyond the immediate research community into the broader physics establishment. Senior physicists who were skeptical about parallel universe theories just a few years ago are now publicly supporting experimental programs aimed at detection. Funding agencies that once viewed parallel universe research as speculative are now treating it as a legitimate and important area of investigation. This institutional support is accelerating progress by enabling larger-scale experiments with longer time horizons. Researchers can now plan multi-year projects with confidence that funding will be available to see them through to completion. They can invest in expensive equipment and sophisticated infrastructure, knowing that the investment will pay off in terms of detection capability. The larger scale and longer duration of modern parallel universe experiments are revealing effects that wouldn't be visible in smaller, shorter studies. Some theoretical models predict that parallel universe interactions accumulate over time, becoming stronger and more detectable as quantum systems maintain coherence for extended periods. Other models suggest that cross-dimensional coupling varies periodically, requiring long-term monitoring to identify optimal detection windows. Both types of effects would be invisible to experiments that run for only hours or days. The multi-year timescales now becoming feasible could reveal parallel universe phenomena that have been hiding in plain sight, masked by the limited duration of previous experimental programs. But extended experiments also introduce new challenges and complications. Maintaining quantum coherence for months or years requires unprecedented stability and control. Equipment must operate reliably for far longer than typical laboratory lifespans. Environmental conditions must be monitored and controlled continuously without interruption. Perhaps most challenging, researchers must distinguish genuine parallel universe signals from the countless systematic effects that can mimic cross-dimensional interactions over extended time periods. Equipment drifts, environmental changes, and subtle experimental artifacts can create false signals that appear identical to parallel universe interactions, if not carefully characterized and eliminated. Solving these challenges requires interdisciplinary collaboration between physicists, engineers, computer scientists, and specialists from other fields. Modern parallel universe experiments resemble major engineering projects more than traditional physics research, involving teams of dozens of researchers with diverse expertise working together toward common goals. The collaborative nature of the work is changing the culture of physics research in profound ways. The lone genius working in isolation is being replaced by coordinated teams that combine theoretical insight, experimental skill, technological innovation, and data analysis expertise. Success requires not just individual brilliance, but effective teamwork and project management. This cultural shift is preparing the physics community for the moment when parallel universe detection actually succeeds. The discovery will require rapid verification by multiple independent groups using different approaches and technologies. The collaborative networks being built around current experiments provide the infrastructure needed to coordinate this verification process effectively. When that moment arrives, everything changes. The question that has fascinated humanity for generations finally gets its answer, and the answer transforms our understanding of existence itself. We discover that our universe, vast and ancient as it seems, is just one reality among infinite possibilities, each as real and significant as our own. The implications stretch beyond physics into every domain of human knowledge and experience. Philosophy, religion, psychology, sociology, all must grapple with the reality of infinite parallel worlds where every possibility is realized somewhere in the vast expanse of the multiverse. But the discovery also opens unprecedented opportunities. If parallel universes exist and can be detected, they might also be accessible in other ways. The same quantum mechanical principles that enable detection could potentially allow communication, information exchange, or even more exotic forms of interaction between parallel realities. These possibilities remain speculative, but they provide motivation and direction for the next phase of research beyond simple detection. The field is already beginning to explore theoretical frameworks for parallel universe communication and interaction, laying the groundwork for technologies that could revolutionize human civilization. The future stretches ahead, filled with possibilities we can barely imagine. Parallel universe detection represents just the first step into a larger multiverse that may contain infinite wonders, infinite knowledge, and infinite opportunities for discovery and growth. We stand at the threshold of this discovery, equipped with unprecedented technological capabilities and driven by the same curiosity that has powered human scientific advancement throughout history. The answer to one of existence's greatest mysteries may be just around the corner, waiting to transform our understanding of what it means to exist in this strange and wonderful cosmos. The search continues with growing intensity and sophistication, bringing us ever closer to the moment when we finally discover whether we are alone in our universe or part of an infinite community of parallel realities. That moment of discovery will mark one of the greatest transitions in human intellectual history, opening doors to understanding that we can barely imagine today. The moment of discovery might not come with fanfare or dramatic announcements. It could happen quietly, buried in pages of experimental data that a graduate student reviews at 3 in the morning, noticing an anomaly that doesn't match any known quantum effect. A pattern so subtle that it takes weeks of analysis to confirm it's real, and months more to understand what it means. This is how science often works. Revolutionary discoveries emerge from careful observation and meticulous analysis rather than sudden revelations. The detection of parallel universes will likely follow this pattern, beginning with tentative observations that gradually build into undeniable evidence through systematic investigation and independent confirmation. The experimental signatures researchers are seeking exist at the intersection of quantum mechanics and information theory. They're looking for correlations that shouldn't exist according to classical physics, patterns of quantum behavior that can only be explained by interaction with systems existing in parallel realities. These signatures would appear as anomalous interference effects, unexpected entanglement patterns, or quantum correlations that persist across greater distances and durations than current theory predicts. But recognizing these signatures requires sophisticated analysis techniques that push the boundaries of what's possible with current computational resources. The datasets generated by modern quantum experiments contain billions of measurements, each requiring precise calibration and error analysis. Finding parallel universe signals within this ocean of information demands pattern recognition algorithms specifically designed to identify cross-dimensional interactions while filtering out countless sources of noise and systematic error. Machine learning systems trained on theoretical predictions are becoming increasingly adept at this challenge. They can analyze experimental data in real time, flagging potential parallel universe signatures for human review while automatically eliminating false positives caused by equipment malfunctions or environmental disturbances. These AI systems are evolving rapidly, incorporating new theoretical insights and experimental techniques as they become available. The combination of human intuition and artificial intelligence creates a powerful detection capability that neither could achieve alone. Human researchers provide theoretical guidance and experimental design expertise, while AI systems handle the computational heavy lifting of data analysis and pattern recognition. This partnership is accelerating the pace of discovery by enabling researchers to explore far more experimental parameter space than would be possible through manual analysis. Recent advances in quantum computing are adding another dimension to this search capability. Quantum computers can simulate parallel universe interactions directly, generating theoretical predictions with unprecedented accuracy and detail. They can also analyze experimental data using quantum algorithms that exploit superposition and entanglement to explore multiple analytical approaches simultaneously. The irony is striking. We may discover parallel universes using quantum computers that themselves might depend on parallel universe interactions for their computational power. The detection and the detector could be manifestations of the same underlying quantum mechanical reality that connects our universe to infinite parallel worlds. This recursive relationship between theory and experiment is accelerating progress in unexpected ways. Each advance in quantum computing improves our ability to analyze parallel universe data. Each improvement in parallel universe detection techniques enhances our understanding of quantum computation. The two fields are co-evolving, driving each other toward breakthrough discoveries that neither could achieve independently. The timeline for discovery is becoming clearer as these technological capabilities mature. Multiple research groups now predict that definitive parallel universe detection could occur within the next 3 to 7 years, assuming current rates of progress continue. This timeline could accelerate if breakthrough discoveries in quantum control or measurement techniques eliminate current technical limitations. But the timeline could also extend if the experimental signatures prove more subtle or complex than current theories predict. Parallel universe interactions might require even more sophisticated detection techniques than researchers currently envision. The signals might exist at energy scales or time scales that push beyond the reach of near-term experimental capabilities. Either way, the scientific infrastructure being built around parallel universe research will yield valuable discoveries regardless of whether parallel realities are ultimately detected. The techniques being developed for cross-dimensional detection are advancing quantum technology across multiple applications, from computing and cryptography to sensing and communication. The broader impact of this research extends far beyond parallel universe detection itself. The quantum technologies emerging from this effort will likely transform multiple industries and create entirely new economic sectors. Quantum sensors with unprecedented sensitivity will enable new forms of medical diagnostics, geological exploration, and fundamental physics research. Quantum computers will solve optimization problems that are intractable for classical systems. So here we are, standing at the edge of the greatest discovery in human history. The mathematics is clear, the experiments are running, and the technology exists to finally answer the question that has haunted us for generations. Are parallel universes real and detectable? The evidence suggests not only are they real, but we're closer than ever to proving it. Within the next decade, we might discover that our reality is just one thread in an infinite tapestry of parallel worlds, each as vivid and meaningful as our own. That discovery will change everything we thought we knew about existence, consciousness, and what it means to be human in this strange and wonderful cosmos.